Hey guys, how's it going? Today I will be defining what we use in the statistical world as a quality control and tying it back to the field of engineering. This process being called SPC. SPC is a process in which it investigates sources of variation within our project. Perhaps our system runs smoothly for an X amount of time, but out of nowhere the quality of the system begins to lack, or things are going out of control and not functioning the way they're supposed to. We can use SPC to have a deeper look into when and why the process is going out of control. But before we get into detail, I will introduce to you guys some things that you need to know and just things to look out for when using SPC. SPC consists of graphs that are plotted over time. This is huge because when we get our results, we want to see when and why the system or project went out of control. Because a graph is plotted over time, we can tie back a situation to a specific point in time in order to get a conclusion. Perhaps at that point of time we did something we don't normally do and it affected the project as a whole. Human error can be quite possible. Or perhaps on that day one of our machines began to give out. The possibilities are endless considering the situations we can all be put in. Whatever the situation may be, we distinguish these causes into two categories: common causes and special causes. Common causes are exactly what they sound like. Things that are common or things we consider normal usually take account for. For example, we can estimate the time it takes for us to drive from point A to point B, and we usually take account that there could be traffic on the way, or quite unfortunately, we catch every red light on the way over there. These are common causes and can be considered normal in our daily lives. Special causes, on the other hand, are things that are out of the normal. We don't wake up on a regular Monday morning and find our tires slashed on a regular basis, or maybe even wake up to a natural phenomenon unexpectedly. These things are not accounted for and considered special causes. Now that we know what we consider disruptions of our system, we can take a look at how they will look graphically. Keep in mind that there must be a minimum of 20 to 25 sample points in order to actually use SPC and most importantly see variability. But before we get into variability, we must use what is known as the empirical rule, which will implement an upper and lower limit. These limits are denoted by 3 standard deviations. Does this sound familiar? This is because SPC graphically looks like the normal curve on its side. Everything within the normal curve or limits is in the clear, but anything after 3 standard deviations is considered an outlier, and in the case of SPC, a special case. Now that we know the nuts and bolts of the process, we can tie it back to real-world applications. When we think of engineering, we have to incorporate the manufacturing aspect of it as well. Perhaps you're in charge of a product and a company introduces you to a new material of some sort that will guarantee you a better quality product and is cheaper. Not only will that benefit you because you save money, but it will benefit your customer because they receive a better product. Perhaps by switching material, you have less products being returned and less customers using their warranty. Tying this back to SPC, we can compare control charts and see if the product is worth changing for. We can pinpoint the amount of outliers and compare the two similar products in a span of time. By doing this, we can see if there's a positive effect in our new product or project. Another way of using SPC, as stated in the beginning of the video, could be by pinpointing why and when the system fails. By using the graphs, we can have a deeper look and make conclusions as to the reasons why there's a negative outcome. This is a good way of resolving a problem before it gets worse. Using the process as a feedback loop where we measure performance and compare its standards, we can act on the situation quicker and possibly change the performance all in a speedy fashion. Thanks to Dr. Walter A. Schuhart, we can use past experience to predict how our process is expected to vary in the future.